Hello everyone, welcome again to the second lecture of Sobolev functions on weighted Rn. And today Dr. Behnam will talk about removal set for Sobolev functions on weighted Rn. Behnam, over to you.
Thank you. Thank you again, all the organizers, for the invitation and being here again. So I will begin with a quick recall of what weighted Sobolev functions were and the two approaches to their definition. And then I will define what we mean by removability of a set, and then talk about a recent work I completed with Riddhi Mishra from JYU, University of Jyväskylä in Finland. Please again, feel free to interrupt at any moment for any questions. So Rn being weighted would mean that we are in Rn with its standard distance, but now instead of the Lebesgue measure, which we denote by dx, we have the measure w dx, where w is a non-negative, locally integrable function on Rn. And then to define Sobolev spaces, we said that there are two approaches. One of them was that H1P on an open set, and again, to emphasize, the weighted measure is closure of C infinity functions in L1, in the Sobolev norm. That immediately produces a Banach space. By definition, it's a completion. And the other approach was going back to the familiar notion of weak differentiability. So this will be LP functions that are, so I have to specify, so this is LP with respect to the weight. And then they are also L1 locally with respect to just the usual Lebesgue measure. And we require that they are weakly differentiable. And this is just integration by parts against the usual Lebesgue measure. That's actually kind of there is a mismatch there. So we don't use the measure here for differentiability part. And we require that weak derivatives, which by definition are L1 log against dx, they also be in the weighted LP. So if both of these spaces sit inside the LP of the weight, so H is here and W is also here. So they are, in both cases, certain subset of subspace of LP. So in both cases, there is two components to a Sobolev function. One of them is some sort of regularity, some sort of smoothness, and the other one being integrability. So in the W1P case, we clearly see that because the regularity part is being weakly differentiable, and then we separately require that the function and its derivatives be in LP. So it's some integrability condition plus some regularity. In the H1P condition, they are more kind of together because the smoothness part is that we can approximate by smooth functions. There is at this moment no notion of differentiation, even in the weak sense. All that we have for the smoothness part is that there exists some sequence of UI such that UI are smooth and they converge to U in LP weight, and that their gradients converge to some function which we denote by delta U, again in LP W dx. And if So this gradient U is well defined, is unique. That means it only depends on U if the weight is P admissible. So I can't possibly go over these definitions of what was P admissible weights and stuff because it will just take too much time. But the minimum we will require in this talk is that the weights are P admissible. In particular, they make this definition okay, plus certain many other properties. So these were the two ways we could approach a definition of Sobolev functions on Rn equipped with a weight. And one case where these are equal is if W is in a P-Mackenhout, then the two approaches produce the same space. So H1P equals W1P. Even if W is P admissible, it doesn't imply that these are equal. There are easy counterexamples. Okay, so I hope that is a good enough recall of what these spaces are. The reason, as a reminder, why we define these spaces is they are needed for certain degenerate PDE. And the reason we leave smooth space is the same as why we leave it in the standard unweighted Rn, because limits of smooth functions in the natural Sobolev norm are no longer smooth functions. But it's also not a pessimistic necessity because we get many good properties for Sobolev spaces, including completeness of the space. We get trace and extension properties, weak compactness, very important for solving PDE. And one other property that I mentioned the other time was that if you have a Sobolev function, then absolute value is again a Sobolev function, and the minimum of two Sobolev functions is again Sobolev in either sense, actually H or W. And there's a nice property that is not shared with smooth functions. Smooth functions immediately fail closeness under these operations. And now today we want to talk about removable sets. And again, this is very unique to Sobolev spaces and is not true for a smooth category. So let's give a definition. So we say a null set E, let's say in an open set, is removable for H1P of omega against this weight if every U that is a Sobolev function on H1P of omega minus E with this W dx is also in H1P of omega. Don't remove E W dx. So that's the definition of removability for H1P, and then we can do a similar definition for W1P. Every function that is in W1P of omega minus E is there. So necessarily E has to be closed so that this is an open set. So technically we have defined Sobolev spaces for open sets. So E is closed. And generally we expect the set to be removable. It is small, and this smallness should be at least the space is the set is null. Because if you say you take an open set and you have a function away from it, now this is not a question of removability, it's a question of extendability, and that's a different story. So we already start with small enough set that it has zero measure. Now, This again fails immediately for smooth category, even 1 point. So U is in C1, just once differentiable omega minus 1 point will never imply that U is actually C1 on all of U, right? You have 1 point, you can have a smooth function that goes to infinity right at that point, and well, it's not a C1 function on all of Rn. But interestingly, for Sobolev functions, it ends up being true that if you are Sobolev outside 1 point, then you are Sobolev on all of your domain. So this question is quite tricky, and again, for continuous functions, even this is not true, as again the same picture shows. This is truly an analysis phenomenon. So there is no analog of this phenomenon in calculus. The closest to this you have seen probably, because this is a complex analysis seminar, I must mention this one, that single points are removable for harmonic or holomorphic functions in the following sense. If you have a continuous function on an open domain, and you know that it is holomorphic, also called analytic, everywhere, except you don't know if it's analytic at this one particular point, then it follows that it will be analytic also at that point, which is used in some key fundamental theorems of complex analysis. So that's the closest you get to this phenomenon in undergraduate courses. So this is really a bit counterintuitive to begin with. And even then, this question still needs some explanation itself. So there are two kind of immediate answers to this question. Just by, if you first see this question, there are two ways that it goes. One way is saying that, let me see which one I go first. So one way of looking at it is that, so two naive answers. Okay. The first one is, of course, right? Because if U is, so let me use this symbol to not specify, am I working with H space or W space? If you are in Sobolev space outside the set E, then U is defined on omega minus E, and just as it is, U is an LP with respect to weight function on all of omega, because Sobolev, okay, so maybe make it a rhetorical question, because aren't Sobolev functions only defined up to a null set? Right? So when you know that U is a Sobolev function on omega minus E, that means it's an LP function on omega minus E. But E has zero measure, so you don't even need to define the function on the set E. And you already have a function which is in LP, because again, integrable or value of the integral doesn't change if you include E or not. So already the function is defined almost everywhere on all of omega, not just omega minus E. So what is the question even? The question, and the reason this is a naive answer, is that it's hidden in the definition. Let's let's say refutation of this one is as follows. Let's look at U is in H1P of omega minus E with respect to the weight. Okay, what does this mean? This means there exists some sequence of smooth functions on omega minus E such that ui converge to u in LP of weight, and gradient ui converge to gradient u in LP omega dx. Both these convergences happen on omega minus e. Well, actually, you can just say even on e, because if you have LP convergence on omega, right? If you have LP convergence in omega, you have LP convergence in omega minus e, again, because it's a null set. So doesn't this mean that your function is actually in LP of all of omega? No, because if you wanted to prove that the function is in Sobolov all of omega, you need approximating functions which are smooth, not just on omega minus e, but on all of omega. And that doesn't happen, as I just showed, even with C1 or continuous function. If you are smooth outside one point, you are not guaranteed to be smooth everywhere. So yeah, the key point is that, but this doesn't mean U is in, so U is in H1P of all of omega, because UI are not necessarily, it could be that they are, but they are not necessarily C infinity on omega. So indeed, just take, you can even take a smooth, so you can take a function in H1P that is already itself smooth. And then your approximating sequence can be just taken to be U itself. But suppose that U is not C infinity on all of omega. So this is C infinity of omega minus E. So then you'll have a function, and this one point is E, right? So this is Rn. So E is just a single point, and you have a smooth function outside of this one point, which happens to be in H1P. It doesn't blow up too fast. So technically, so UI you can take to be the constant sequence, and that proves that U is in H1P. But the same sequence UI doesn't imply that it is in H1P of all of Rn. If it happens to be the case that my function is at the end of the day again in H1P of all of omega, you need a different sequence. In one point will end up being removable. So in this picture that I have, just to give you an idea of how we prove that this is actually in H1P of all of Rn, so you take approximating functions to be like this. So you truncate at some point and stop going to infinity, because then you cannot get a smooth function. So you truncate at some vicinity of this one point, and you call the function ui, and then you do this truncation at higher and higher levels. Now you will get a sequence of smooth functions, not just on omega minus e, but all of omega. And then these happen to again converge in LP to my u. So that is how you would end up proving that u at the one point is removable. So that is the first answer to the question, is showing that why it is not obvious. It's not a question of defining if or extending if or u here. So the function is already defined almost everywhere. It's about the smoothness part. And also notice that integrability will never be an issue. Again, the set is null. And the naive answer too is no set is removable because they are not removable for smooth category, right? So smooth functions are dense in H1P. So if something was removable for Sobolov, so it should be removable for them. But as my answer, as my picture just illustrated, as that shows, some sets, singletons, for example, are removable. Although they are not removable for smooth category, they are removable for Sobolev functions. And this is actually a flexibility property for Sobolev function. It's a nice thing that you don't have to confirm something at every single point of a domain, unlike C1 or smooth categories. It's very, if you have practiced with smooth functions, it's always scary. You always have to care for every single point. You cannot glue functions easily. You're always worried. But with Sobolev functions, this is a nice feature that if you have some kind of limiting process and you know that the behavior is nice outside, say a counter set, and if you end up proving that the function is Sobolov outside that counter set and that counter set is small enough, then it follows that, well, you have a Sobolov function globally. So this is the kind of uh, process that where you end up knowing a function is Sobolov, but except for some exceptional set. But then if you know some removability results, you can bypass that. Okay. So with this was mainly using the H1P definition. Let's look at it won't be my main focus, but for kind of completeness, it's important to mention that. So removability for W1P space would mean. So let's see what this would mean. That if we have, so let's isolate the integrability part here. It's the regularity part. So if we have integration by parts on omega minus E, then do we have it for omega? And this time you can see that the question is obviously not the same. When you have this set E and you take a function, on omega minus E. So when you say integration by parts, so for omega minus E, your test function, so for weak differentiability, you check integration by parts against test functions, so are compactly supported on omega minus E, which means in particular that they vanish. So you're testing against functions which behave like this. So they vanish whenever they approach E. So you only test integration by parts against such functions. But when you allow just the set E itself again, we do not require anything about E or just vanishing near E. So you see that if you have checked that the integration by parts holds for all functions compactly supported omega minus E, by no means does it mean that it will hold for all functions, because, well, it's just not easy, right? So with W space, removability is basically asking, does integration by part holding on complement of E also imply it on all of omega? With H1P space, removability means if you can approximate a function by smooth functions outside E, can you approximate the function by smooth functions on all of omega? And that's the story of removability, and it has been studied throughout literature because it has practical and theoretical importance. The earliest removability results are with, not surprisingly, with unweighted Rn, and the default definition has been the W1P. So one of the key properties of W1P space, maybe advantages, is we define it with Lebesgue measure. The weak derivative is using Lebesgue measure, and there we have Fubini's theorem. And here, Fubini's theorem helps us prove the following. If projection of E onto each hyperplane of one codimension has a measure 0, Lebesgue measure of measure 0, so that is the Lebesgue measure n-1, then E is removable. Removable for W1P. Okay, and this is believable because let's go to this picture here. So you have integration by parts everywhere away from E. And you know that if you project your set E onto this, it has measure 0. So now you do Fubini's theorem, what happens? In Fubini's theorem, you see that almost every line actually never contains any point of E. And then the integration by parts was okay away from E. From that, you can conclude that the function is, the integration by parts still holds. And the same for the other direction. Or you can, actually, this is kind of use this idea to prove the ACL characterization. A function is Sobolov if and only if it is absolutely continuous on almost every line, and the derivatives the directional derivatives end up being in LP. So again, integrability part is always there, but now if you have a projection with 0 measure, that means almost every line actually never meets E. So if you are Sobolov on the complement of E, you're absolutely continuous on almost every line that doesn't meet E. But then E's projection has measure 0. That means the same statement remains true even if you included E in the domain. So this includes a lot of large sets, right? So even you can have sets of infinite Hausdorff-1 measure whose projections onto the axes still have 0 measure shadows, right? Geometric measure theory stuff. So some big sets indeed end up being removable. These are not attributed to anyone because they are probably very easy from definitions. So around 97, there was a work by Koskela who showed that if you have a porous set in hyperplane, then it is removable. So these contain some parameters. So porous is actually P porous, then it's removable for W1P. So he studied looking at sets which lie in the hyperplane. So already your set is contained in one copy of Rn-1, and one dimension is here. So he looked at sets here with, obviously the interesting part would be that Ln-1 of the set is positive, because otherwise it follows from the previous observation. So the set has n-1 dimensional measure positive, but it's still removable because it is porous. It has a lot of holes in it. And this porosity is needed because a single line segment, for example, in R2 is not removable, because you can have a Sobolev function which is 0 on one side, to the one side of this segment, and is equal to 1 on the other. And this function is locally constant, so it's Sobolov outside the line segment, but it is not Sobolov on the with including this E because almost every line is not absolutely continuous. It's not even continuous. Um, you wouldn't be continuous on these lines, and these are not negligible collection of lines because it's a whole bunch of lines filling a whole segment. So you see that continuous, like codimension one connected sets are never removable. So anything here which would have some interior wouldn't be removable. So that's why porosities are very natural conditions when it comes to removable sets. So that was Koskela 97, but around similar timing, Yang Mei Wu proved a more general thing. So not necessarily hyperplane sets. So porous sets with a different definition of porosity imply removable. And yeah, she didn't have any restriction on being necessarily in the hyperplane. And again, these are in unweighted cases with the definition W1P. In fact, proof by Pekka is using the same idea of looking at all the parallel lines going down here and here. So what he proved was that if you are porous, then the limit going from above matches the limit going from below for almost every line, therefore proving absolute continuity on almost every line. When you bring in the weight, remember, this will all go away because you don't have this absolute continuity on line characterization and because it depends on Fubini's theorem, and Fubini's theorem is not available when you have arbitrary weight. So the weight could be large here versus here, and Fubini just fails. So what is this kind of? So we our work is kind of an extension of Yang Mei Wu's result to the setting of weighted Rn. And our methods are way more involved again because we have a weight, and some of the techniques in Yang Mei Wu are not applicable, which I will explain. So what does this porosity look like? I have some prepared some pictures to show you, but before that, maybe you can ask any questions.
If I have missed it, did you already define what are porous sets? Or
No, I didn't. So I will. So in these, so it's kind of, porous is a meaningless word now because it's being used again and again. So the definitions in these two references are different. And the one that I will define in our weighted case is generalization of this one. So our definition that I'm about to give will reduce to this definition when you take weight to be just one. That means unweighted, basically, unweighted array. So when you take our weight to be just one, we will end up coinciding with this definition. So I'll give it in a second with a picture.
okay, thanks.
Yeah. For now, you just imagine that if a set is small, it's removable. But the point is that the smallness here is not necessarily in terms of Hausdorff measure. Hausdorff measure cannot characterize removable. Some small dimensional Hausdorff sets are not removable. And on the other hand, some rather big dimensional Hausdorff sets end up being removable. So Hausdorff measure cannot predict removability. It's more about both the size of a set and how its geometry works. And that is exactly this notion of porosity. So let me maybe zoom this out a little bit for you to see better. Okay, so you have this red dots, which is my to be removable set. And I required the following, that at different stages, so given K, so on, I have a collection of cubes. So there is this cube, a collection of finitely many cubes in K. And the cubes, their union contains E. So I like writing this. So the union of all cubes in QK covers your set E. And then there is a frame, there is a ring under each one of these Qs such that it does not pick any point from my removable set. So it's away from that. So these will be the green parts. So every cube has some buffer zone around its perimeter, which is away from my set E. And the thicker this ring is, the better, right? Because then I have a thicker buffer zone. So I take this ratio of the length or width of R divided by length of Q to be alpha. So this is a number between 0 and 1. And usually it's very small, usually almost 0, because it's more and more difficult, right? So you want to cover these, and these are disjoint cubes, so they don't touch each other. So just as my picture shows, anything you see in the picture is what it is. It's finitely many, the rings are there and they cover it. So, and then when you go to the next K, you want a more refined picture. So these cubes, actually the way I drew this picture was copy paste from above and then delete the green parts and put these blue parts. So there we had maybe 4 cubes and now we have 8 or something. So I didn't want to clutter my picture. So the idea is that these are inside the previous ones. So previous level were here with this ring too thick. So maybe this was that. And now we have, instead of that, we have 2 different cubes. But then this subdivision makes it possible to have more refined, thinner cubes like that. So there is this telescoping feature that these cubes are nested inside the previous generation. They become smaller, but still they cover this set E and they have rings. So now the rings are in blue, right? And it's tinier, so we don't see that much. So this is the starting point, that you have such a covering. Now, what is our particular porosity condition? So I have the S bigger than P. We say E is SP chorus if, first of all, measure of this union of QK converges to 0 as K goes to infinity. This measure, remember, is the weighted measure. You integrate against the weight W. That's kind of a very natural condition, but the more technical condition is this. So you have these alpha. So you fix a K, and then you over all the cubes in QK, you have alpha. This alpha depends on the Q. So it can change from one Q to another. If you want more uniformity, you can say that all alphas at level K are the same. And then here you have S, which is my parameter from above, S minus 1 here. And then here there's another number C1. This is a structural constant that I will explain. So that is for those relative thickness of the rings. And then you have measure of the ring. So this R means matched to this Q. And then you raise it to the power S minus P divided by S minus 1P. Okay, you calculate this over all the cubes of level K. You get some number. And you raise it to a negative power, which is 1 minus S. And then you do this over all k. And you want this to diverge. You want this to be infinity. So this is, of course, a backward thing. So you prove your theorem, and then from the proof, you recover what is needed for all your calculations to go through, right? So these two, if they hold, we say that the set is SP porous. So in the standard unweighted Euclidean setting, you can take P to be 1 because P will be the P of P admissibility. Remember and then the smaller P is, the better for us. And so the best P is 1, and in the unweighted Euclidean setting, 1 is possible. So you take P equal 1, and this actually simplifies. So if this is 1, this is 1, they cancel. So there is no power here, and other parts also cancel. You can take C1 actually to be just, I believe, 1. Yeah, you can take it to be 1. So it simplifies a lot. So let me just write it here. If P equal 1 and W is just 1, this recovers or reduces to the Yang-May-Wu's condition, porosity condition. If you check her paper, just keep in mind that then S is named P in her paper. So it's like P1 porosity. Okay, now maybe it's time to write down the main theorem of interest. So
can I ask something before that?
Sure, sure.
So how should I think of a porous set? I mean, intuitively.
Okay. So you should think the following way. These become infinitesimally small, right? All the cubes and their rings. So these measures mu go down to 0. And alphas could remain, they don't have to go to 0, but usually they also shrink. So this is controlling like how much the relative thickness of these rings are. If quantitatively in this divergence sense, you retain good buffer zones for the rings, you will be able to remove the set. And that should be expected because the more space you have, the more you are able to extend the function. So we will extend the functions from the ring. So we will extend the function from the green part into all inside of the Q. And the thicker this is, the cost of this Sobolov extension will be smaller, right? So this condition, this summation, is saying exactly how much control do you need to make it work. If you look at the asymptotics of this summation, you see that with bigger alpha, it's easier to get equal infinity. It's a bit complicated because this power is negative, then the whole thing is to a negative power, and alphas are smaller than 1. So if you run this negative times negative times negative, you see that this summation is increasing in alpha. So if alphas remain big, you're more likely to be divergent.
So, I mean, maybe we are trying to somehow capture the idea of a finite set. I mean, for finite sets, this probably could be done.
Yeah,
So,
yeah, exactly.
Okay, thanks.
Yeah. There was this picture I said you truncate, right? There was one point where the function blew up, and I said truncate at a smaller and smaller level. Yeah, it's trying to do the same. In each level, you imagine there's just one point problem inside the Q. So you want to extend, and the extension Sobolov extension has a cost, and to control that cost, you need this precise divergence condition. So indeed, if you have this condition, so this we just put out in May, is that suppose W is a P admissible weight. P, remember, is always bigger than 1 on Rn, n bigger than 2. Then every SP porous set is removable for this H1S space on all of our NWDX. There are some there are some variations and facts about removability. For example, if you are removable for Rn, if you're removable for one omega containing your E, then you're removable for any other omega as well. So in general, without loss, you only take omega to be Rn. These are easy stuff because if you can remove inside here, then you glue it to the outside. So it's never a big deal. So this is really not just saying it's removable on Rn, it's removable for any open set containing. And that's the main theorem. So make sure this makes sense on your end. And n has to be at least 2 because in R1, usually nothing is removable because 1 point disconnects your space. The same phenomenon that I mentioned, you can have totally different behavior on the two ends of line segment. In R1, 1 point is the hyperplane, so you can have arbitrary behavior on the two sides. So you need at least n equal to. So that is the result. And again, it reduces to Yang-Meiwu's result in unweighted Rn, but the techniques we have are completely different because none of the techniques that Yang-Meiwu uses basically can be applied here. And again, the idea is that you want to, so the idea is actually really cool. So let me go back to my picture and explain how does one even start proving such a result, okay? You have a function that you know is Sobolev everywhere outside this set E, right? You begin with a U that is in H1P omega minus E W dx. Think even about the standard like unweighted case. So your function is good everywhere outside E, but you want to say it's also actually a good function if you include E. The idea is very nice. You sacrifice first the function on a bigger set. You say, okay, you know what? I'm going to take my function everywhere. Remember, it's defined on all of our n. But now I'm scared of the set E, and I actually stop before hitting the set E. I want to stop when I reach the boundaries of these cubes, okay? So now I'm looking at the function, which is defined everywhere outside the union of the set's cube. So I make sacrifice. My function is defined everywhere, but I say, okay, let me just consider it on Rn, which is just omega minus union of qk. And then I Sobolov extend into the cubes. And that extension happens from the ring. I have a function defined on the ring. And remember, ring is a very nice Lipschitz domain, even smooth except for the corners. And I extend the function by hand. So I ignore what you remember is defined here, even inside Q. But I ignore that and I say, instead of U, I want my favorite U. I extend it in a Sobolov way and I get a new function, which is the same as U outside the cubes, but it has now new values inside the cubes. And this depends on, of course, level K. So I get a UK, and that becomes a Sobolov function The benefit is now it's all of Rn or all of omega, not minus dx, because I did it by hand. I know it is in all of this, right? And then the porosity condition comes here. So if you have the porosity condition, you do all these nasty calculations and you realize that this is a Cauchy sequence, or after maybe a sub, you pass to a subsequent, it has, let's say, oops. So this has a Cauchy subsequence inside H1P. Okay, but what was the biggest benefit of moving to Sobolev spaces? Completeness. That means after passing to a subsequence, you know that this converges to some function. Let me call it U bar in H1P of all of our n. This is all of our n because UKs were Sobolev on all of our n. Now I have a function defined on all of H1P. But look, U must be just U because they are equal almost everywhere. U bar here is U, and this is just U. But then you move to the next and next generation. So anytime you are not in E, at some point you will be not in the cubes. So in some next generation, right, you will be here, and this will not be in any of your cubes. So it will be equal to U for all the tail of the sequence. So you have proved that U belongs to H1P of all of our n. And that's and now initially you started actually with U1S. Well, S is bigger, so this part was okay. The reason you have to go down to P is to get this Cauchiness there. But now you have a UP function, I mean H1P function, plus from the beginning, you know that the integrability is actually better. It's LS and then gradient belongs to. Gradient U is also LS integrable. So you have a Sobolev function H1P, but you know that both function and the gradient are more integrable. This means that you are actually in H1S, not H1P only with the weight. And that's a proof. That's a proof. And all of that porosity condition is backward recovered from what do you need to get this Cauchy thing. So let me just show you a picture of the type of calculation, and that will be it for today. And that C1 in the porosity definition is what is the constant, Sobolev extension constant. Yeah, so here are the calculations. So after you extend, you get the Sobolov norm. You can see here that I have norm on Q versus norm on R. So, and similar one is true for the gradient. Then you subtract and you calculate the Sobolov norms. And yeah, that condition implies we have a Cauchy sequence. So here comes this. It's all backward calculation. You just see what works. And once you have it, you get a Cauchy sequence for this and that, and from that it follows. Yeah. Thank you so much for your attention. And
Thank you for the wonderful talk. Do we have any question?
So can we, I mean, somehow, probably not, but can we somehow generalize it to W1P removability?
yeah, so this question was part of our learning process. So initially we were trying to do with W1P, But then we realized an example that I showed the previous session. So if you take this function minus n plus 1, then u is not weakly differentiable. And remember, weakly differentiable requires only, is with respect to Lebesgue measure, because the gradient of this wouldn't be locally integrable. So on any ball that contains the origin. So, but if you take your weight to be absolute value of x to gamma, and gamma is a positive number, I think it's np minus 1, I think. Then this u ends up being in h1p of the ball. U is not in W1P of the ball because it's not weakly differentiable. However, U is actually in W1P of B minus the origin. The only problem is at the origin. Actually, this function, all of these with respect to weight. So what happens is that weight is vanishing at 0 with some big power, and it forgives this non-integrability issues. And it forces them to end up in W. So what this means, this means that the origin, so it means that the 1 point origin not removable for W1P. And that is kind of a dead end, because if you cannot have 1 point removable, what else can you? And then I must mention that this weight is actually P admissible. It's a nice weight. It's not Mackenhout weight. It can't be, because we know with Mackenhout weights, H1P is equal to W1P. In particular, from our result, if your weight is Mackenhout, we have actually proven W1P removability. But we see that the moment you leave the Mackenhout class, things are very different. And this basically says that study of the removability for W1P is, I want to say, is meaningless. Let's say it's delicate.
I see. So it seems that the only hope is to now categorize which subsets of W1P can be removable, or something like that.
So you want a
Or maybe
subspace
that
of
is not so
W1P?
I mean, even for a single point, the whole W1P, I mean, there are functions in W1P for which the singularity still remains there.
Yeah.
So therefore, maybe we can try to characterize subsets of W1P for which sets are removable or something like that. Or I don't know, maybe that's not important.
The thing with the W1P is it's a fake kind of use of the measure. The measure is never there except for integrability. Your definition it doesn't use the weight. You use Lebesgue measure to talk about differentiability, and then you use the weighted measure to talk about integrability. So really, this W1P space, the fact that I think in literature it is the default space, is because at the end of the day it's equal to H1P. And one of the main theorems everyone proves right after introducing them is prove that the smooth functions are dense in it, which is the same as proving that H1P equal W1P. And when this is not true, then bad phenomenon happens. So I think the right approach, the right definition of Sobolov spaces in the presence of weight is actually H1P. It's the more intrinsic one. To kind of bring more evidence for this, H1P equals the Newtonian space, N1P on the metric measure space Rn, Euclidean distance weighted measure, which is very intrinsic definition. And for that reason, again, it's another indication that H1P is the right space.
Okay, thanks.
Yeah, you're welcome. Thanks for questions.
Okay, anyone? Any other question? Okay, so I have one like curious question regarding the when a Cantor set is porous.
Mhm.
So like there is a result in like in R in one dimension, which says that if you take a Cantor set in R and if it is quasi-conformally homogeneous, then it is porous. Do we have any kind of relation in higher dimension with quasi-conformal homogeneity and porous of Cantor set? Like when a Cantor set will be a porous? Miss, I mean, have you seen any kind of result like this?
In the paper, we give some examples of Cantor sets that are removable, just to illustrate that this condition is useful.
Mhm.
I'm not sure if the definition of porosity, and I have very little expectation that that porosity will be similar to this one.
Okay.
So that makes it very, very tough. But I can say that Sobolov removability, one of the biggest motivations for studying it is actually coming from quasi-conformal theory.
Yeah.
Because you want to know if a map is quasi-conformal outside the set, is it conformal everywhere? So
Yeah.
that's called quasi-conformal removability. We took a great amount of time explaining this motivation in the paper. So if you want this link between Sobolov removability as quasi-removability, you can find the references from our paper.
Okay. Sure. Thank you. Okay. Any other question? Okay. So if not, let us thank our speaker. Thank you,
Thank
Behnam.
you.
Thank you so much for giving such a
It was
wonderful
pleasure
lecture.
these 2 weeks, and hopefully in future again.
Yeah, sure.
Bye
And I
bye.
must say, thank you so much for accommodating yourself with the Indian time because it
No,
is
no, my
quite early there.
pleasure. It's my moral and professional duty.
Thank you so much.
Yeah.
Thank
Bye
you.
bye.
Bye.